Today, we're going to break down the vision transformer, or ViT, one of the most important ideas in modern computer vision. We'll start with a plain English explanation, work our way through the actual mathematics, and finish with a fully worked numeric example. So by the end, you'll understand not just what ViT does, but exactly how the numbers move through it. Here's our roadmap. We'll start with the intuition, a simple analogy for how ViT looks at an image. Then we'll talk about why anyone thought to bring transformers, which were built for language, into computer vision. From there, we'll get precise with a formal definition and the architecture diagram, then go step by step through the math: patch embedding, position encoding, self-attention, and the MLP. We'll ground all of that in a worked example with real numbers, and close with when ViT wins, what it costs, and the key takeaways. Here's the core intuition, and it's simpler than it sounds. Think of a photograph as a sentence. ViT slices the image into small square tiles, like cutting a photo into puzzle pieces, and each tile becomes a visual word. The model then reads the whole sequence of tiles, exactly the way a language model reads a sentence. It asks, how does this piece relate to every other piece? By the end, it's built up an understanding of the whole picture, enough to say, this is a dog, or this is a bicycle. Notice what's missing here. No convolutions, no sliding filters, just patches, positions, and attention. So why do this at all? Transformers had already taken over natural language processing. Think BERT, GPT. The authors of ViT, Dosovitsky and colleagues, asked a simple question. Can the same idea, self-attention over tokens, work directly on images with minimal vision-specific machinery? Convolutional networks come with built-in assumptions. Nearby pixels matter most, patterns repeat across the image, which makes them efficient with less data, but their receptive field grows slowly, so relating far apart regions takes many layers. ViT drops almost all of that. Self-attention lets any patch connect to any other patch in a single layer. The trade-off is that ViT needs a lot more data to learn those patterns from scratch, but given enough scale, it matches or beats CNNs. Let's make this precise. A vision transformer is an image classification architecture that does 4 things. First, patchify. It splits the image into fixed-size, non-overlapping patches. Second, embed. Each patch is linearly projected into a d-dimensional vector, and a learned position embedding is added so the model knows where each patch came from. Third, encode. A stack of L transformer encoder blocks lets every token attend to every other token. And fourth, classify. The final state of a special learnable class token is passed through an MLP head to produce the prediction. Everything we cover from here on is really just unpacking these 4 steps. Here's the whole thing laid out visually. On the left, the image gets cut into patches. Those patches, plus a prepended CLS token, get turned into embeddings with position information added. That sequence flows into the transformer encoder, which repeats the same block L times. Layer norm, multi-head self-attention, a residual connection, another layer norm into an MLP with GELU activation, and a second residual connection. Whatever comes out the other end goes through an MLP head to produce class probabilities. Every arrow on this diagram is something we're about to define mathematically. Let's start with the math. An image X with height H, width W, and C channels gets reshaped into N patches, where N equals H times W divided by P squared, P being the patch size. Each patch is flattened into a vector and multiplied by a learned projection matrix, E. Then we prepend a learnable class token and add a position embedding EPOS to the whole sequence. That gives us Z0, the input to the very first encoder block. This is the only place in the whole architecture where the image's 2D structure gets touched. Everything after this is just sequence processing. Each of the L encoder blocks follows the exact same 2-stage recipe. First, take the previous state, apply layer norm, run it through multi-head self-attention, and add back the original input as a residual connection. That's Z prime. Second, take Z prime, apply layer norm again, run it through the MLP with GEU activation, and again add back the residual. That's Z for this layer. Layer norm always comes before the block, and the residual connection always comes after. That pattern is what makes it possible to stack these blocks very deep without the gradients vanishing. After the final block, we take the class token state, apply one more layer norm, and that becomes our image representation. This is the single most important mechanism in the whole model. From the input X, we compute 3 learned projections: Q for query, K for key, and V for value. Attention is then softmax of Q times K transpose, divided by the square root of dk, all multiplied by V. The division by the square root of dk is just there to stop the dot products from getting too large before the softmax, a scaling trick that keeps training stable. What comes out is, for every patch, a weighted blend of every other patch's value vector, weighted by how relevant they are to each other. That's the whole idea of attention in one line. We don't run just one attention operation. We run several in parallel, called heads. Multi-head attention concatenates the outputs of H separate attention heads, each operating on its own smaller subspace, and projects the result with a final weight matrix, WO. Running multiple heads lets the model track several kinds of relationships at once. One head might specialize in color, another in shape. On the classification side, only the class token's final normalized state feeds into the MLP head, followed by softmax to produce the prediction. And just so you have a sense of scale, the original paper's base model uses 12 layers and 12 heads at 86 million parameters, while the huge model scales up to 32 layers and 632 million parameters. Time to make this concrete. Take a tiny 4x4 grayscale image with pixel values 10 through 160 and a patch size of 2x2. That gives us exactly 4 patches. Flattening each patch turns it into a 4-dimensional vector. Patch 1, for instance, becomes 10, 20, 50, 60. We then linearly project each of those 4-dimensional vectors down to a 3-dimensional embedding and add a position vector, giving us E1 through E4. The sequence class token, E1, E2, E3, E4 is what actually gets fed into the transformer encoder. And inside that encoder, self-attention is what lets every patch exchange information with every other patch. Let's go one level deeper and actually compute attention with real numbers. To keep it simple, imagine just 2 patch embeddings in 2 dimensions. x1 equals 1, 0, and x2 equals 0, 1, with the weight matrices for Q, K, and V all set to the identity. So Q, K, and V are just equal to X. Step 1. The raw scores are Q times K transpose, giving us a score of 1 for each patch attending to itself and 0 for attending to the other. Step 2, we scale by 1 over the square root of dk. Here, dk is 2, so we divide by about 1.414, giving 0.707 and 0. Step 3, softmax each row, which turns those scores into 0.670 and 0.330. Step 4, the output is that softmax weighting applied to V. So patch 1's output becomes 0.670 times x1 plus 0.330 times x2, which works out to 0.670, 0.330. Notice what happened. Each output is now a blend of both inputs, weighted by relevance. That blending, repeated across every patch and every layer, is the entire mechanism that lets ViT understand a whole image. So where does this actually pay off, and where does it struggle? On the strength side, ViT gets global context from the very first layer, since any patch can attend to any other patch immediately. It scales extremely well with more data and compute. It shares a simple, uniform architecture with NLP transformers, which means techniques and pre-trained backbones transfer easily. And it underlies a lot of today's multimodal models, like CLIP. On the limitation side, because it has so little built-in inductive bias, it needs large pre-training datasets. The original paper used JFT300M to reach its potential. Attention cost also grows quadratically with the number of patches, and if you train ViT from scratch on a small dataset, a CNN will typically beat it. It can also lose some fine-grained local detail because of the fixed patch grid. Let's bring it all together. 1. An image is just a sequence of patches, Treat it like a sentence of visual words. 2, Z0, the class token, plus the patch embeddings, plus position embeddings, sets up the input sequence. 3, self-attention. Softmax of QK transpose over the square root of DK times V lets every patch exchange information with every other patch. 4, we stack L encoder blocks, each with multi-head self-attention and an MLP wrapped in layer norm and residual connections to build up a deep representation. And 5, the class token's final state feeds a small MLP head to produce the prediction. That's the vision transformer, from plain English to the exact math. Thank you.